Given f of x is 5x plus 6 and g of x is 2x squared minus x minus 1, find the composite function and then find the domain of each function and the composite function. Okay. So first, we need to find the actual composition. So I'm going to write it on this side. F of g of x is written as f of g of x. So first, you want to do the inside of the parentheses. So here we get f g of x is given by this right here. So that's 2x squared minus x minus 1. And now we need to evaluate the function f at 2x squared minus x minus 1. So that means that we're taking all of this and plugging it in for this x in the function f. So here we get 5 times 2x squared minus x minus 1 plus 6. Simplify, distribute this 5 inside. So we get 10x squared minus 5x minus 5 plus 6. So this is 10x squared minus 5x plus 1. So the composition is equal to this right here. Then it says to find the domain of each function. So the domain of f, notice here that this is just a line. So my domain would be negative infinity to positive infinity. There's no fractions, there's no square roots, and there's no logarithm. So the domain is always negative infinity to positive infinity. And then the domain of g, is there any fractions? No. Square roots? No. Logarithms? No. This is a parabola. So it's going to open something like this. So which will use all the x values. So negative infinity to positive infinity. And then it says to find the domain of the composition. So we look at the definition. The domain is x such that x is in the domain of g, and g of x is the domain of f. It is important to realize that the product of the functions f of g is not the same. Okay. So this is the important part. The domain is going to be x such that x is in the domain of g. So the domain of g, remember I said it's the second function that you have here that we have to take an extra look at. So to find the domain, we can write this in 2 steps. Number 1, find the domain of each function, which we did right here. Number 2, identify the second function listed. So for example, in our example here, we have f composed of g of x. So the one that we're going to focus on is the second one here. So the domain of g is negative infinity to positive infinity. Then we're going to find the domain Then we're going to find the domain of the composite, which is your answer. So my composite was (10x squared minus 5x plus 1). So if we look at this answer, this is a parabola, so the domain is going to go from negative infinity. So I'm going to write this as a composite, negative infinity to positive infinity. So your domain is going to be is the intersection. In other words, what they have in common for step 2 and step 3. Okay, so here the domain of G is negative infinity to positive infinity. So that's what we get for step 2. And then for the domain of the composition, we get negative infinity to positive infinity. So we ask ourselves, what does this have in common with this? Well, they have everything in common. So the final domain of the composition is negative infinity to positive infinity. So we always need to make sure that we're checking step 2. And you'll see why it's important in the next example. So f of g composed of x is f of g of x. So if I plug in g of x is 1 over x. And now everywhere I see x in the function f, I'm going to replace with 1 over x. So we're taking this and plugging it in for this x. So we end up with 4 over 1 over x plus 2. We want to simplify. So one trick here that we can do, well, one way to simplify this is to add these two together. So you would have to find a common denominator and then divide 4 divided by that. Or we can multiply every single term by the denominator here. So I'm going to multiply this by x and this by x. So this becomes 4x divided by x times 1 over x is 1 plus 2x. So my composition is equal to 4x divided by 1 plus 2x. Okay. So to find the domain, again, the first step is determine the domain of each function. So here the domain of f, since we have an x plus 2, we set that equal to 0. So negative 2 can't be in the domain. So my domain will go from negative infinity to negative 2 union negative 2 to infinity. And then for g, here's g. X is a fraction, or 1 over x is a fraction. So we set the denominator equal to 0. So 0 can't be in the domain. So this domain will go from negative infinity to 0, and then 0 to infinity. And then the third domain that we need is the domain of the composition. So notice that the composition has a fraction. So we set the denominator equal to 0 and solve for x. So subtract the 1 and divide by 2. So negative a half can't be in the domain. So my domain will go from negative infinity to negative a half union negative a half to infinity. Okay. So now to find the actual domain, we want to look at the intersection of the second function. In this case, the second function is g. So I'm going to look at g. So I'm going to look at g, and then I'm going to look at the intersection of the composition. Okay, so we want to see what they have in common. So I'm going to draw a little picture here. So the domain of G is everything except for 0. So it's everything here except for 0. And then the domain of the composition is everything except for negative a half. So here's negative a half. and then it takes everything. So you want to see what they have in common. So what they have in common is basically we cannot use 0 because 0 cannot be used for the first one. It can be used for the second one, but not the first one. So 0 is not common to both. And then -1/2 cannot be used for the first one. So since it's not in both, then we can't use the -1/2. So my domain is going to be everything except for 0 and -1/2. So I'm going to go from -infinity to -1/2, union -1/2 to 0, union 0 to infinity. Okay, so again, if I draw a better number line here, this is for the domain of G. It's everything except for 0. And then for the composition, it's everything except for -1/2. So we're going to use all of this, but when we get to -1/2, we cannot use it. And then when we get to 0, we cannot use it.